subject assignment in libraries is often labor-intensive and complex, especially with systems such as LCSH that has subdivisions and free-floating terms. So research shows that AI performs better with structured vocabularies like FAST, subject facets. So in our project stage 1, we tested the FAST assignment through the OpenAI API with OCLC fast reconciliation. In stage 2, we adopted a fast vector database, and we are now in stage 3, AI-assisted subject and description generation for text, image, and multimedia collections. So in comparing stage 1 and stage 2, the main difference is the validation method. Stage 1 relied on the OCLC fast API, while stage 2 shifted to a local vector database. The overall workflow using Python and the CALA remained the same. So we initially tested the workflow on the Florida Solar Energy Center collection in the IR. We experimented with GPT 3.5, that's in 2024, and GPT-4 with and without fast reconciliation. We also extended the workflow to mark-based collection, such as owner thesis and ETDs in OMA. So this is our data flow diagram. Our team worked with programmer Eric to develop a workflow integrating the OpenAI API for generating fast headings and keywords, along with OCLC's reconciliation service for validation. The process begins by reading a book's title and summary from an Excel file using prompt. The OpenAI API generates fast topical headings. These headings are then validated using OCLC's fast link data API. If valid, the heading is saved to an Excel file. If invalid, suggested fast headings are reviewed, and ChatGPT selects the most suitable ones based on the title and the summary, which is then output to the file. So this shows our prompt construction. We define the role as library cataloger, adjusted the number of terms generated, provided examples, and ordered terms by importance and set restrictions. OCLC's reconciliation service is occasionally unavailable, so we explored alternatives. We downloaded the full fast topical dictionary and built a local vector database to test the semantic subject assignment. So using OpenAI's text embedding 3 small model, we generated embeddings for fast headings. Queries are matched through similarity search, returning contextually relevant subjects rather than just keyword matches. So this retrieval augmented generation RAG-based approach improves accuracy and reduces irrelevant headings in batch processing. This slide shows the OpenAI API and vector database workflow. So after building the fast vector database, we used each record's title and summary to retrieve 25 semantically similar headings. ChatGPT then selected the best 5 in context. This ensures high-quality input while eliminating reliance on OCLC reconciliation and simplifies the workflow. And the database was later repackaged for cloud storage where Google Drive allowing librarians to install and run it using provided instructions. It was first applied to over 8,000 ETDs, enabling scalable metadata enrichment about 4 seconds per record. Later, it was extended to other IR collections, including the teaching and learning with AI conference materials. Here heat map shows ratings of the vector database approach by discipline. Most fast headings were valid, with only 8 out of 75 records rated as somewhat valid. Mainly because the OCLC, the fast, the database, it has obsolete terms. Overall, 68 records showed medium to high relevance, with 46 rated high. So science and social science had the most relevant headings, while humanities had lower relevance. Overall coverage ranged from comprehensive to moderately comprehensive, with humanities showing some gaps. So for our project stage 3, AI-assisted subject and description generation for multi-model collections, the following technologies were used in our testing: GPT-4, GPT-4o, 4o mini, text embedding 3, small model for vector database, and Whisper through OpenAPI for transcribing audio files to provide the text base for subject analysis, CV2 for OpenCV for extracting frames from video files, and the Base64 for encoding images to be sent to the API. So next steps including updating the knowledge base, seeking programming and funding support, expanding collaboration among librarians and AI developers, and strengthening human in the loop workflow for quality control and scalability. So these are some of the previous project talks, and this is our project team. And thank you very much. And if you have any question, feel free to unmute yourself.
Thank you, Sai, for this very practical way for us to think about how to use AI in the metadata work. Do you have any questions from the audience or comments? Please feel free to unmute yourself. Yes.
Yeah. Hi, thank you, Sai, for sharing your experience in the projects. So I'm just curious because I'm from a medical library. I'm from the health science library. So we do have a backlog of student ETDs, electronic thesis and dissertations. So I just wonder if your project can be, because I think you're mostly using LC subject headings, right?
Yeah.
Is it possible to adapt for the mesh headings? I'm just curious.
Um, it there needs to be you can build like a mesh knowledge database, like a vector database. Yeah, you can use the second method. Yeah, and using API, to generate headings, and then you need to go through the mesh knowledge base, the vector database to do for the validation, and then to generate the headings. And yeah.
Okay. Yeah, I might refer my cataloging librarian to connect with you. I know she's trying to use AI to
You need
create some kind of script.
I think you need a programmer for help. Just
Yeah.
a librarian, might be a little bit challenging. You probably need
Mhm.
a programmer for help because it has
Yeah.
both system set up and
Yeah.
everything.
Yeah. All right. Thank you.
I'm really glad to hear this conversation. We're already make some new connections here. So this is the purpose of our conference. We don't have time for another question for Sai, but please feel free to leave messages in the chat.